Another really important aspect of stellar evolution and planet formation is basic temperature stuff. Just hot to cold. Pretty easy. Thermodynamics, I don't remember which law it is, but it states that the hotter object always loses heat and heat only flows in one direction. It only goes from the hotter to the colder. If you have a hot star, the heat flows out of the star into outer space. That's very simple. Outer space is basically a vacuum, so it technically doesn't have a temperature, but I mean, I guess if it could be called a temperature, the particles are so sparse that they barely bounce off of each other, and when they do, they travel a large average mean distance, meaning they don't touch another particle for a long time. I don't want to go into that, but anyways, outer space can be considered to be like maybe 2.73 Kelvin, somewhere around there, 3 Kelvin, I can't remember. That being said, the temperature principle of stellar evolution, August 27th, 2016. In this paper, it is explained that stars' surfaces cool as they evolve, therefore leading to a general principle of stellar evolution according to stellar metamorphosis. In this theory, a star of 6,000 degrees Kelvin on its surface is much younger than a star which has a surface temperature of 4,000 degrees. Subsequently, a star that has a surface temperature of 3,000 degrees Kelvin is younger than one with a temperature of 2,000 Kelvin. Just so there is no confusion, the surface temperature only applies to the star itself, not if it is being heated by an outside body. So if you have what the astronomers call a hot Jupiter in orbit around a large blue star, and the blue star is 25,000 Kelvin, and the hot Jupiter is being ripped away, and hot Jupiter is like 6,000 degrees on the surface. No, I'm not saying that the hot Jupiter is a star that's 6,000 degrees Kelvin. You have to take into account the fact that that star, the hot Jupiter, is being heated by the very large blue O-type star. This only applies really to a star that produces its own heat, and that's very important to understand. It produces its own heat, like a campfire. Campfires are hot because they produce their own heat. You don't have another campfire over here on the opposite side of your backyard heating the campfire over here. No, it's the temperature of the campfire, meaning this applies to the temperature of the star itself, not if it's being heated from outside body. Okay, I think I beat that into the ground enough. The principle only stands for stars in isolated areas not impacted significantly by hotter hosts. Okay, and as well, the principle only accounts for surface temperatures, meaning the surface temperature of Neptune is below the melting point of nitrogen, but this does not mean Neptune is very young because its internal temperature is well above 6,000 degrees Kelvin. All this being said, the principle is as follows. The surface temperatures not impacted by outside bodies will drop as the star evolves. So not necessarily from the beginning where I have in here, oh, well, if a star is 6,000 degrees Kelvin, it's younger than one that's 5,000 degrees Kelvin. It's not as cut and dry as that. It's more or less like a continuum. And this leads into the transformation curves that I have in a much further paper. Remember, this was written in 2016, and I've yet to update it. But the more important aspect of this, I'll get into real quick. But just so the reader is made aware of the enormous inconsistency of establishment astronomy, one only needs to look at the classification of stars, in which only the stars which have temperatures above 2400 degrees Kelvin are considered actual stars, and very, very old stars which have cooled well past that are ignored and relabeled planet, brown dwarf, or exoplanet. And you can go on Wikipedia and find this stuff. It's all over. Here's a little graph. Of course, I'll link this paper to the bottom. Now you notice it cuts off at around 2400 degrees Kelvin. That doesn't make any sense for them to cut it off at 2400 degrees Kelvin, because outer space is like 3 Kelvin. And we all know, according to basic thermodynamics, the hotter goes to the colder. The heat will flow out of the star. forever until the star dies. There should be stars 2300 degrees Kelvin, 2200, 2100, 2000, 1900, 1800, 1700, all the way down to where the star finally comes into equilibrium with outer space, the temperature of outer space. And that not only is on the surface of the star, but internally as well. Of course, you probably have to destroy it in order to get the internal regions exposed to outer space so it can lose its heat. But that being said, here's the Willinski-Taylor, and this isn't Willinski-Taylor. This is one of the original graphs as well. Notice how it goes like this, and they have all these stars, and you have your absolute magnitude over here, and you have your classification. The Harvard classification is the big fancy B, O, A, O, F, O, G, O, K, O, M, O, and the O can be O 1, 2, 3, 4, 5, 6, 7, 8, I believe, or to 9. So it would be like a BO is like the biggest, hottest one, and then B1, B2, B3, B4, B5, B6, and then it would go A1, A2, A3, and all the way down the line. But anyways, look at that down there. You notice how you could just it's pretty simple. These are ABCs for astronomers, but it seems to just right over their heads. Check it out. All you have to do is draw an arrow, and that's exactly what I did in the another previous Willinski-Taylor diagram, but this is the Hertzsprung-Russell diagram, and boom, it just keeps on going, which means these highly evolved stars have temperatures cooler than 2400 degrees Kelvin. The astronomers call the stars that are below 2400 degrees Kelvin, they call them planets. Of course, it's very, very strange. Anyways, I think that's basically it. This the temperatures. This is a whole big thing all by itself. I need to go ahead and review this paper and just clarify more of it, and to make sure that I put a new graph on here. Clearly, this is an outdated graph as well. See, what else did I want to say? I guess that's about it. All right, you guys. Today is October 3rd, 2019.